Hello everyone, my name is Kushagar Mathur. I'm working as a research associate in the Building Planning and Building Technology Department, also known as BPT, in the Berlin University of Arts. For the past few months, we have been working in a project by the name of GEnEff, in which we are trying to assess building energy efficiency using innovative demonstration methods using simulation and VR. In today's presentation, I will be telling you about a paper that we published in a conference in which we explained how we developed an interactive virtual reality VR simulation environment in which the user can also get a thermal feedback in the climate chamber that we developed. In past few years, there has been lots of research going on in VR environment. And our building sector department is also not untouched by it. There has been some applications in augmented reality in which you can see the whole building designing process in augmented reality process. There has been some VR models in which you can see how an urban city is being planned. There is also a big example of Google Earth VR in which you can actually in VR environment, you can visualize different large cities model in a quite good detailing. And then there's also examples or some softwares which are available which a user can use in which you can visualize different parameters of a building on the building site using different augmented reality technologies. There are also some examples in which you can physically experience virtual reality environment. For example, Birdly is such kind of an example in which you can experience a full body flying like a Superman or like a bird. There is also an indoor workout experience which is developed by VirZoom, in which you can use your own home bicycle and can have a virtual reality effect of driving this bicycle on the roads. There's also experiments going on with how you can actually feel the thermal temperature differences or sensations of different temperatures on your body, on your face, and also there is a suit from Tesla. There is a suit called Tesla suit. It contains a full body sensation of the heat, cold, and also haptic feedback. If we look at our current building energy simulations, a user has to draw a 3D model in a software using 2D plans or a real building, and he has to simulate it giving different parameters and then wait for the results and do the simulations again, change some parameters and do the simulations again. But these simulations have certain weak points, like for example, it's not immersive for the user who is making these models. The user doesn't feel or gets disconnected by the actual building. For this case, we have an improvement that the user can actually look the building in the VR environment and can have a better decision-making factor or can have a better insight of the building. There's also no interaction with the model that's currently possible. The user cannot see what the changes would be if a window is opened for the whole night, or if the door is opened, or if there is no insulation in the wall, how the building will be behaving. For that case, we have an improvement that there is a real-time user interaction that's possible, for example, switching on the lights, opening the windows, etc. There is also no climate experience in the simulated values. The user does not feel the climate of Brazil if the user is making a building in Brazil, or if in Moscow or in Sahara Desert. And then therefore we have an improvement option that in our climate chamber you can also feel different climates of different continents or countries. In our research approach, we started with the VR model in which a user can interact we made this VR model in Unity. We connected this VR model with our thermal simulation model in which is in Modelica. It's a bidirectional communication in which if a user interacts with the VR model, the signal is sent to Modelica using UDP, and UDP Modelica reacts with the signal. For example, if the user is inside the building, outside the building, a window is open, the user sets the temperature to a certain degree, Modelica receives it, changes the energy balance of the building, and sends the values back to the to Unity, so that the Unity can visualize it and the user can visualize also these values in VR environment. We extended this value using our climate chamber. In the climate chamber, we are using normal consumer-based devices to manipulate the temperature values, to manipulate the airflow, mass flow, to represent the sun values. These air conditioning devices are controlled by remote control using infrared signals. We hack these signals and we are using Arduino to control these devices. The Arduino is being controlled by OpenHub, which is a home automation software. OpenHub is, you can program rules, different rules in OpenHub, which are basically logical methods or logical operations. OpenHub is getting information from Modelica, which it is using to perform logical operations. If the air conditioning has to be switched on or off, the humidifier has to be switched on or off. If there is a sun outside, Modelica sends the numerical values to OpenHub. OpenHub receives it, compares it with if the sun is too strong outside, if the sun is from Sahara Desert, or if the sun is from Brazilian countries, then it receives the signals, compares it, and turns on the radiator in such a way that it can be felt by the user. For our first experiment, we are using a basic VR environment, which is a simple office room by 3 by 3 by 3 meters. It has a window and a door. For aesthetics, it also has a computer with a coffee mug and a chair in it. Of course, there are different interactions that are possible. For example, setting the heat temperature or cooling temperature. There's a lamp inside which can be turned on or off. The presence of user is also counted, and of course the window and the door can be opened, or the window can also be tilted and completely opened. For our thermal room model, we have connected it with external boundary conditions so that we can so that different climate locations can be considered. This room model sends the information to Unity and OpenHub using UDP data transferring protocol, and then Unity and OpenHub can reuse or use this data in different kinds of methods. For the climate chamber, we have a base construction of almost 60 centimeters. This igloo or this climate chamber is constructed in such a way that it shouldn't be so difficult to deassemble it and reassemble it again. It has 2 ring tubes in the base construction, both of them for carrying cold and hot air, and it's made in such a way that there should be as equal distribution of air inside the igloo. Both the air conditioning units is outside, and these air conditioning units are supplying hot or cold air depending on the requirements. Before the air conditioning unit, there are also 2 quick changing actuator or valves. When the OpenHub sends a signal of getting warm air, the warm air actuator switches on, so we have warm air inside the igloo. When it's with cold air, similarly the cold air actuator switches on, and the warm air actuator switches off, so that we don't have both the air inside the igloo. But there is still a possibility that we can have hot and cold air together inside the igloo for different experimentations. We are using OpenHub because OpenHub is an event-based system. When there is an event, for example, there is a change in the temperature value, OpenHub receives the signal and runs the rule every time when there is an event. There's also a possibility that OpenHub's event bus can be connected with the REST API, and this REST API can be sent information from outside, and actually that's what we are doing. We are using Python libraries, which is getting signals from Modelica, and then it's being fed into the REST API of OpenHub. OpenHub also has an option that it can be controlled with serial binding. We are using this binding for controlling our Arduinos. Also, in OpenHub, there's an option of web interface using which a user can see the values, can also interact with different devices. There is an option for buttons. There is also an option for list menu. And with the new update of OpenHub, there's also an option for having graphs in the web interface. We have different configuration for our devices right now. It's the same as what we have in our VR model. If we have a door on the left side and the window on the right side, we have a table, we have a chair in which the user can sit. We have 3 different temperature sensors which act as a feedback to OpenHub, telling OpenHub what is the temperature, what is the real temperature inside the igloo. We are using 3 temperature sensors to minimize the layering effect of different values or different temperatures we have. For experimentation, we took a really simple test scenario in which a user goes into the room at 9 a.m. in morning, sets the heating temperature to 22 degrees. Again, the climate location which took is of Berlin. Opens the windows at 11 a.m. and closes it after 15 minutes, and then works or do his job till 3 p.m. and then cross-ventilates the room for 10 minutes and then leaves the room at 4 p.m. On the right side, we can see the same graph of 24-hour simulation, and on the left side, the bottom graph is the real-time factor, which actually visualizes how you can use the simulation for real time, in which 1 second in real life will be 1 second in the simulation, or there's also a possibility that you can make it faster, 20 times faster, 100 times faster. On the right side, we can see that there are still the dynamics of the domestic air conditioning units that we are using. It's not so great because they take almost 5 minutes to change the mode of their air conditioning, or they also don't supply cold air in such a low temperatures that the environment or the air temperature of the igloo really changes so quickly. On the graph below, we can see when the cold air is supplied and when the warm air is supplied, depending on the temperature differences we get from the simulated values and the real temperature inside the igloo. This is again the same example, but this is in Egypt where the climate is hot outside. And on the right side, we can see again the graphs are really close. The values that the OpenHub is really trying to get the red and green line, which is blue line is the simulated value, and green line is the real temperature from the climate chamber, and the blue line is actually the simulated value. And we can already see that the OpenHub is already working and trying to minimize the distance or the area between these 2 lines. This is a small video. Because of Corona, we cannot ask anyone to go inside the climate chamber for testing reasons. So I hope this video will just give you a brief explanation how the interactions and how different how the user can interact with the VR environment. in conclusion, we can say that the immersive and interactive VR simulation approach works, even though the dynamics are still limited because we are using not laboratory air conditioning units, but domestic air conditioning units. There is also an option for improving control strategy. We are just using PID controllers right now with feedback and switching off and switching on. There could be a possibility to have a threshold in which certain the air conditioning unit works till certain temperature and then switches off. For example, there is also option for adding more parameters like, for example, moisture control, solar radiation control, air velocities, and other things. We can always add different VR scenarios. Since we are using Unity for virtual reality, we can have multiple zones built of a building, in which one zone could be air conditioning, the other one could be not air conditioning. In future, we will be implementing surface radiation using Peltier elements. We already did some examples or some testing, as you can see in the on the diagram on the right side. We will also we are using Peltier elements because it can supply heating. It can be heated and cooled in the same way if we just reverse the polarity of the Peltier elements. I hope I was able to explain everything well to everyone who was listening to this presentation. But still, if you have any questions or comments, please feel free to contact us. You can also contact Professor Christoph Nytsch-Geusen using the email ID that's present in there. Thank you very much.